postdoc researcher in based in Leiden University in the Netherlands in the group of applied quantum algorithms. He obtained his PhD in 2021 in Barcelona Superconducting Center by University of Barcelona, all in Spain, under the supervision of Jose Ignacio Latorre and Arturo Garcia. His works has focused on quantum machine learning and implementation of algorithms in the near-term quantum computers. His current interests are efficient representation and manipulation of quantum states, analysis of VQE, and capacities of machine learning models. So let's welcome him.
First, thank you very much for the invitation. It's always a pleasure to be in contact with new people and new researchers. So I would like to talk now about this quite recent work called Reduce&chop, about how to take a deep circuit, a deep problem, and try to mimic its behavior using shallow circuits. Of course, this is going to be biased towards I speak, and you're trying to listen. But please, if there is anything you're not following, or you don't understand, or it's not entirely clear, stop me, interrupt me, and ask at any moment. Okay. So as we were discussing in a moments ago, this work is about how to use the scarce resources available that are right now existing for a quantum computer, in order to exploit as much as possible these resources and try to solve problems that are obviously not reachable within our capabilities. So in this work in particular, we are focusing on taking deep quantum circuits that are not fitting in a quantum computer because of the coherence, or because the T1, T2 are too large, and there are not so many operations that one can fit into the computer. So we're taking these deep quantum circuits and we are reducing it via classical operations into shallow circuits, so that these shallow things fit into the quantum computer and then are not simulatable, but they can be computed in a quantum machine. So this work, which is the vertical line that you're seeing on slide, is fundamentally different from all other works that are more in the horizontal line. Like, for example, these two references that I'm giving there. In fact, the first one is by one of my colleagues in the group. Take a look at it if you want. It's quite interesting. But the main difference is that in this case, we are not simulating the correlations among two different quantum things in a classical way. The works in the horizontal line, basically what they are doing is substituting the quantum correlations with some other classical operations, like, for example, entanglement forging, or, like, for example, having different computations in parallel. But in our work, this is going to be much more brutal, because we are not cutting in qubits. We are not simulating entanglement. We are cutting in layers. So in any case, we are going to destroy all superposition and all entanglement, which is, as when I started, I remember this rule, the step to never make, right? So I was told when I started, at the moment you measure any quantum state, you're going to destroy all the information, you're going to destroy all the superposition, you're going to destroy all the entanglement, and then everything in that quantum state is lost. And that was like a mantra that appeared in the standard research. But now, since we don't have any other option, because the hardware is not as good as we would like it to be, then we might be in the position of exploring this non-orthodox way to split quantum circuits. So the motivation is quite standard. So in the case of the horizontal lines, quantum computers are limited in the number of qubits, and we are looking for all this classical way to overcome these difficulties. That would be, as we were mentioning, force entanglement, parallel execution, or this approximate equality of several small systems plus the correlations are giving one large system. This is, for example, what happens in classical simulations such as tensor networks. In our case, in this case in particular, we're talking about having quantum computers that are limited in the number of layers that are available. This is the number of operations that one can consecutively apply. And in order to overcome this problem, which has been way less explored than the limited qubit scenario, we can go for efficient compilations, which is an MP problem, but it has a certain limit. So there's an optimal result that one cannot overcome. And we are going to go to sequential executions, and that is the goal of this work. So the main question is, can we do that? Or better said, in which case can we do that? Is there any scenario where shallow circuits can efficiently, and this efficiently is extremely important, can efficiently mimic deep ones? We are going to see. In general, this is not going to work, and this cannot work because there exists a classical bottleneck, which is one of the main problems in the field of quantum computing. So describing an arbitrary quantum state, we know that it's exponentially hard because we have to perform either quantum tomography, which is exponentially hard, or we can use some sort of strategies such as classical shadows so that only partial information can be retrieved. Not everything in the state, but just part of it. So even in that case, we are only describing a small part of the quantum state. That's in the download side. In the upload side, we know that creating an arbitrary quantum state may require, depending on the state, but may require exponentially many gates. Creating approximation might be a little bit cheaper. Even if we go to the Solovay-Kitaev theorem, it can be only polynomial, but that's only in a special case. And then another question is how to find the way to create a particular state. Any classical combination of quantum computers must present exponential overhead in general, because we know that, well, it's the well-known course of dimensionality. We have too many parameters to take care at the same time, and this is not efficient. This is it lies at the core of quantum information processing. So in general, we know that all the exponential menace is all around us, but even though in general this is not possible, we can still think of any cases of interest where we can still exploit scarce resources to perform, let's say, good calculations, where good is taken with a lot of quotes, and it's telling you, well, what kind of how close we can be to a certain computation of interest. So after all this introduction, let me present you this method, this reduce and chop, right? So put yourselves in the following scenario. We have a quantum algorithm which is really, really deep. And it is so deep that it cannot fit into a quantum computer, right? In this way, our red-ish box will be the quantum computer. Is there any colorblind person that cannot follow my red, blue, green things? Okay, perfect. Then the red-ish box will be our computers. Will be our computer, and it can fit a particular depth. The entire algorithm does not fit, but half algorithm does. And then what we can do is split this algorithm in halves and then run the first half, measure, and with this outcome of this measurement, run the second half. All the results are combined classically, right? So in principle, each of these parts is efficient. We can compute U1, we can compute U2, we can measure, and everything is efficient. The problem comes from the fact that this measurement, the measurement after the first half of the circuit may imply exponentially many options, and we have to take all of them into account. So this is where the exponential, yeah.
Sorry, so what is D? The depth?
Oh, D is the depth.
So your time goes in that directions from left to right.
Yeah, my time goes left to right, exactly.
Okay, good, thanks.
So left to right and top to bottom.
Sorry, quick question. So how to decide the cut? I mean, do you have special cut strategy, or you just find the blocks you should cut?
Okay, so the optimal cut strategy in that case, it's split it right in the halves, right at the middle of the algorithm. Why? Because in that way we minimize the required depth in the quantum computer.
Okay.
There might be, this is optimal in this particular metric. In other metrics that we can discuss later, there might be a different optimal cut. But in order to know this optimal cut, we need to simulate the entire circuit, which is not efficient. So we don't want to go into that realm. It's going to be much more difficult. So we stick to this optimality in depth, which means cut right in the middle. Okay.
Okay, I see. Okay. Thank
also, following this argument, notice, and this should not be overlooked, notice that there is this question mark at the end of the reddish box. This question mark is going to be as a free space that we're going to use later. So take that into the entire framework. In terms of a little bit more mathematical description, what we are doing is essentially something really similar to the Feynman path or Feynman simulation of quantum computers, which is instead of having this U, computing this probability X of measuring a particular bit string after the execution of one circuit, we want to split this in halves, and obviously this equality here is exact, right? Because we are just having some realization of the identity, and we can now see mathematically what these claims of round first half, measure, and so on means. Basically, what we are doing is executing this first bracket, be U1 0. This can be executed efficiently using, for example, Hadamard tests. We can measure the second bracket efficiently as well. And we measure, prepare it, and so on. Everything is efficient, but there is exponentially many depth, many Ds. This is where the bottlenecks come from, right? So what we are going to do is to use the free space in the question mark to reduce the complexity before the chop. That means, imagine that for some reason there exists some transformation which is shallow, such that most of the B's are zero. That is, only a few elements contribute actively to this P of X. In that case, if the number of zero elements is sufficiently large, then this computation stops having this exponential overhead and starts being efficient. And we can achieve that with this operation. Now, the entire work is going to be in which cases we can find a shallow circuit such that this reduction is feasible. And this is the great question. And in general, we know that there is there's no general theory for sure. We would like to have, but we didn't. And this is going to lead the entire discussion of this work, right? So in order to formalize this concept, I'm going to talk about some new concept called the computational basis CB epsilon rank. This sounds a little bit exotic and a little bit convoluted, but in the end, the only thing that we are counting here is how many elements we need in this red square, how many elements we need for this sum. This is modulo small details, the computation, the CB rank of one particular state. In definition, how many elements in the computational basis exist, are needed to represent one state within accuracy epsilon. Of course, there might exist any other, any other basis rank. And what we are doing with this R is moving from the basis where we are interested to the computational one, or at least this is the goal of this thing. There exists an optimal representation, well, a representation that minimizes maximizes the overlap between one state and another state with a given computational basis. And that result is basically take the largest coefficients in the computational basis and just store them. So discard everything which is below a certain threshold. This computational basis rank is extremely important because even though it does not make easier to compute each of the terms, like these terms here, this bracket, it tells you which ones we should compute, and it is telling us how many, not how many, but which few of them among an entire ocean of different bit strings we need to compute. So if we know these things, this computational BCB rank, and we know which bits we have, then this computation is efficient. In terms of maths, in terms of a proper definition that you can see in the paper with no constraint, the CB rank is basically as follows. So in case this psi is a quantum state with n qubits and epsilon is a real number, then the epsilon approximate CB rank of a state is whatever integer number we need so that this overlap is larger than 1 minus epsilon. And this state here, this psi k, has at most k non-zero amplitudes. The best possible representation, what we were discussing before, is this thing. Just keep the largest elements, and this largest is given by the permutation pi, because we are going in descending order. Those are the main ingredients that we need. And now we're going to discuss in which cases this approach to reduce and chop can give us an interesting result and can give us some method to effectively reduce the complexity of simulating a probability.
Could I have one more question about this computational basis rank? So, okay, so this definition is the state-dependent definition, right? So your computational basis really depends on the given state that you are simulating in the beginning.
Yeah, well, the computational basis is a property of one state.
Okay. Okay.
Like you could compute the entropy of one state or whatever. This computational basis rank is a property of the state.
Okay. Okay. Good. Thank you. Just want to make sure.
Okay. So first of all, something that is not might look trivial, but it's not. How to estimate this CB epsilon rank? And I'm telling you just in advance, it's only possible to do that if the CB rank is small. And let me give you the explanation. In order to estimate this CB rank, the best thing that we could think of, the best recipe is just sampling from one state and then estimating how many elements are needed to represent the state with a particular accuracy. The problem is that in general, the one state generates a probability distribution with exponentially many elements. And we must sample from this probability distribution. if we want to sample from this probability distribution with a given number of samples, the requirement is that the number of samples has to be at least exponential. But in that case, we are not efficient. Sure. So we are going to fix our measurement budget to be M. In the case the CB rank is smaller than M, then with this many measurements, we can have an accurate description of the underlying probability distribution, or at least of a big part of this probability distribution. That is the one that is relevant. Everything else is just discarded. I don't know what is there. What is there in the discarded part? I just know I'm not interested in it. In the case the CB rank is larger than M, then it cannot be estimated. And the intuition is quite easy. So imagine that I have M samples for the uniform superposition of 2 to the n. So I'm sampling M times, and I'm having M different results. So how can I possibly distinguish between the uniform superposition of all exponentially many gates and only the ones that I have seen? And the answer is there is no possible way of doing it. So this is limiting our scope where this can be applied, and this implies a requirement for the concentration of probabilities. And in fact, this requirement of concentration of probabilities can be formalized mathematically as we can estimate the CB rank to be a number k with M samples only if this this lemma, this failure probability holds. That means imagine that I'm sampling capital M times, from which only small m times are not in our candidates, in the k most relevant ones. So the chance of underestimating the CB rank is smaller than this quantity, which is quite small in general. There are some requirements on how to perform this sampling, because it comes into conflict with some deep axioms in the theory of statistics and probability. But without coming into nasty details, just bear in mind that we can only estimate the CB rank if we are measuring many times in the interesting part of the state. The second consideration is about the reducer R. Just the most immediate question: does R exist? We are not sure about it, and we are not sure under which conditions. There exist for sure some conditions for which R must exist. For example, take absolutely any product state, and then we know that with local operations we can reduce any product state with any CB rank to just CB rank 1. For example, just a uniform superposition applied Hallamans, and then we can transform that state into the 0 with CB rank 1. But of course, this is a very easy example. So does it hold in general? Well, there's no fixed answer. Our guess is probably not, but there are some arguments for this condition to hold, in at least in some cases, that give us a little bit of hope towards finding the proper reducer. The arguments are as follows. So first of all, there is always a trivial solution, which is the reducer is the first half of the circuit inverse, like E1 dagger. Of course, this is absolutely trivial, but the depth of R and E1 will be now the same. And if you remember from the previous from the original description, what we are doing is basically passing all the complexity of the circuit to the second half. So we are not doing anything. This trivial solution is not giving anything of interest. There might be a shallower solution, because we are not interested in inverting all the states. We are just interested in inverting one of these states, the initial one, for instance 0. And there are exponentially many options, exponentially many gates that satisfy the second bullet and not the first one. So that gives us some hope that there might be shallower conditions. Even more, we are not interested in absolutely inverting the initial state. It's enough with approximately inverting, in the sense that we go from a 0 of CB rank 1 to something with low CB rank. That will be enough for efficiency. And even more, we are not interested in having this equality strict. It's enough with having some approximations. So these arguments give us hope to look for a shallow reducer. Further observations is that if we have this reducer and this reducer exists, then we only require the CB epsilon rank in the middle of the state, that is right in the where the reducer happens, to be small. And this is, for example, if we can compare it to other methods, like for example MPS or classical tensor networks, this is more general, because tensor networks must be efficient at all steps, while this reduce-and-chop has to be efficient only in one step. So there is room for interesting cases. So these are the two ingredients that tell you, well, reducers or this reduce-and-chop can exist. Not sure, but they can exist, and they are also more general and more interesting than existing classical methods for simulation quantum computer. So we are in uncharted territory. We're exploring something new, or at least we have arguments to see it in this way. The last part of these considerations is, well, what states we can represent. And since there is no general theory, we cannot know that we cannot give a proper description of these states, but we can argue and we can have an idea of what we could do and what kind of states we can represent. So now, please. So I'm going to describe several sets of states. The first one is this calligraphical U, which is the set of all states generated by circuits, by a family of circuits. That's it. These U epsilons, epsilons 1, epsilons 2, are the set U plus all states at distance at most epsilon from there. And here you can see that the sets are growing. Of course, epsilon 2 is larger than epsilon 1. These CBK states are all the states that can be reduced to a low CB rank with some reducer. And again, this K2 is equal than K1. Then the only states that we can represent and that we can reduce with this method are those lying in the intersection of this group. Some of them will be absolutely trivial, like they already have low CB rank and you have to do nothing here. Some other imply finding a reducer that moves the state from this area, for example, into the low CB rank area. And this is another problem that we have to discuss in a minute. But in general, only the intersection between the states that we can create with our ancestors and the states that we can reduce, only in that intersection we are doing something interesting. How to mathematically describe this intersection is still an open question. So now the hard part of it, which is how can we look for a reducer? Because those are trivial, but what we don't know is how to move from these states to these other states. This is just a quest for the reducer. And since we have absolutely no idea of how to do that, we go to the answer that almost always works, which is go variational. That's it. End of the discussion. So we are studying with this U1 that is God-given, and we can optimize some reducer that depends on certain parameters, and make the optimizer minimize this quantity, the CV epsilon rank. But there is a problem here. There's a catch, which is the CV epsilon rank is not always estimable. So you can do that only if the CV rank is already small. So standard methods cannot work because it's not as easy as just calling some scipy.optimize.minimize function and say, please take this function and make it smaller, because this function itself cannot be computed. So the optimizer is not going to digest this function. It's absolutely impossible. So we need to create a tailor-made optimization method so that the optimizer is capable of dealing with this problem. And the only way of doing that is by keeping the computational basis rank low at all steps. So in order to do that, what we have done is designed a scheme where this U1 is gradually activated, or almost adiabatically activated, not exactly, but step by step, so that we have under control the number, the CV rank that exists, and this never goes over a certain threshold. It's basically a cut and thrust strategy. So basically we start here for some U1 that depends on some parameters tuned so that it's 1. So the CV rank is 1. And then we start activating the ansatz. At some point, there will be a moment where the CV rank is above a certain threshold. At that moment, then we stop with the activation and we start the optimization, right? So the CV rank starts growing, reaches some point, goes down with the optimizer, and after this is complete, then we can grow again. So it's basically a juggling thing. We give a little bit from here, optimize, give and optimize, give and optimize, and at the end, when this t is equal 1, we end up activating with the entire ansatz. We activate that, and we have reached the final stage without going at any moment above a certain threshold of the CV rank. Of course, this method assumes that this kind of path exists, which is not always guaranteed but the numerical simulation that we have conducted show that there are cases where this can be done. So I know that I have told you that there are many possible problems and that there are many cases where not everything is guaranteed, not so many theory behind that. And you might be thinking, well, is this any useful? Is this going to help in any case? And what I can show you is, well, I don't have the theory, but I have the numbers, and I have some numerical experiments that I can show you to showcase that there are there are instances where this reduce and chop can work. So the numerical experiment that we have conducted is basically as follows. So imagine this transfer field Ising model inspired ansatz as given in this scheme, and for the unitary gates that we're going to mimic, and imagine a second part, which is the hardware efficient ansatz for the reducer. The goal, the inspiration behind this problem is basically U is inspired in an existing problem, so it physically motivated, and it's not fully general. So that gives us a little bit of advantage in the sense that, well, it's not as expressive as it could be. On the other hand, the reducer, that has to be shallow, concentrates as much expressivity as possible in a small number of layers. I'm not interested into the number of parameters. Like, I can add as many parameters as I want. The problem here is the number of layers. So the complexity of the reducer is going to be larger than the complexity of the ansatz. I would like to give you the details of the experiments here. We have done some optimization of the reducer using CMA strategies. It's some sort of genetic algorithm. And we have reduced our complexity requirements from 40 to 24 layers of entangling gates, which is almost half, and that might set the goal of what is achievable with a quantum computer closer to our times. We have tested it for 18 qubits because we have to go for numerical simulations, and there are some instability problems that still need to be optimized. And we have always imposed the complexity requirements of having a number of samples, which is polynomial both in qubits and in the accuracy allowed. And we have considered two different activation schemes for the optimization: one linear activation of parameters and another smooth activation of the one. And I would like to show the difference between the two activation schemes. First, in the smooth activation scheme, what we're doing is some sort of adiabatic change from identity to the U1, and you can see all this behavior that I was explaining to you before. Like, focus, for example, in this image F. You can see that I'm increasing the optimization. I'm increasing the CB rank by activating the ansatz, and at some point at the threshold, which is marked by this dashed line, we start with optimization and reduce the CB rank. And this process is repeated several times. In the case of the F, which is very mild, there are not so many repetitions because the accuracy threshold that we allow is quite large. So we don't have to be extremely precise. However, in some other cases, like for example, figure D with a much smaller accuracy, you cannot observe this behavior because it's really, really small, but I can tell you that exists. Yeah, maybe I would like to give a little bit of explanation of these images as well. So all the gray lines are different instances of this problem. The black solid line is the average of all of them, and the red line is the one with latest convergence, so the hardest one. And you can also see a number, I don't know if it's large enough, but this number 1 minus f, which is 1 minus the fidelity, the average fidelity of all the possible instances. And notice that this number is always smaller, always smaller than the epsilon at the caption of each figure. So observations from the general results is the smaller epsilon is, the more difficult is to reduce this, obviously. And in fact, at some point, the only thing that we can do is to keep the CB rank estimable, but reduction is not that attainable anymore. Same we can observe with the difference between 8 and 10 qubits. The larger number of elements is going to make the optimization much more difficult. The smooth changes in CB epsilon is what we commented before. It's way easier to see in large epsilons. This is some sort of adiabatic activation scheme, but the story is entirely different if the activation is given parameter by parameter linearly. You can see here that this is much more unstable. It has larger increasings in the CB rank at each new activation of the parameters, and larger decreasing of the CB rank as well, because it's quite easy to compensate. So that gives rise to this spiky behavior. This imposes much more iteration than in the smooth activation, but still it's more efficient in the sense that each new step can make the CB rank decrease dramatically. However, since this is way more chaotic, it's more risky in the sense that we can fit into an area where the reducer cannot be found. So is it that it cannot be found, or is it that it just does not exist? This is an open question. In general, in some other features that we have discussed, this scenario and the previous one are quite similar. And just for comparison, I would like to mention that there is possibly some optimal activation scheme that is more experimentally friendly and has some smooth behavior, not so chaotic. Probably there would be any, and there might be chances to find it. But in this case, it's just I will just give you an heuristic recipe with no formal guarantee of working. And I would like to highlight that the only methods available for this kind of optimization are evolutionary methods and not gradients. And we can discuss about it later. But bear in mind, gradients are not available in this case, basically because of the chaotic behavior of the landscape, which, by the way, we have no idea how the optimization landscape looks like. And this is something that people from classical optimization appreciates a lot, and we are not using it. This is also related to some other works. But at least with all these problems, I have showcased that in the particular instance that we have considered, we have found a solution using this reduce-and-chop algorithm. So just to wrap it up, I would like to give a little bit of an overview of how to extend this reduce-and-chop to other problems. There is obviously one branch that is easier, that can be tackled more or less easily, which is the decision problems. Why? Because in complexity theory, all few-qubit problems or few-qubit decision problems are robust in the sense that these are problems that work with an oracle, and this oracle is, I give you the right answer with probability 2/3. This is the standard formulation, but this 2/3 is completely arbitrary. It can be any number above 1/2 with certain details, but basically there are statistical tools that allow you to have any number above 1/2 is enough for these decision problems. So that makes the accuracy not so important. It doesn't have to be very, very small, and this method is then suited for this kind of cases. Some other possible spin-offs are how to represent quantum states efficiently. These states that that only need a small number of elements in the computational base, and that includes efficient compression of quantum states or representation of quantum states in different bases at the same time, which is not quite standard, but it is feasible. I assure you it's feasible. And another different branch is, for example, using this px which is computing a probability, to sample from a probability distribution. This can be done via known metropolis-like algorithms, and that allows you to use expectation values, to compute expectation values for this state using this method. And if you can compute expectation value, then there is a place for optimization problems and searching of ground states. So just to conclude, to put all the list of all the important messages that I would like you to keep for at least until Monday. So this work presents a simulation of these circuits using shallower ones, which is quite novel. It implies a reduction of the complexity in terms of layers, not in qubits, which is the standard way, and that there are, in general, exponential overheads that should prevent us to make this work, but we have presented an heuristic machinery to avoid these exponential overheads and partially solve them. All the bottlenecks in the optimization of the method have been identified, and we have provided methods to try to overcome them. Not guaranteed, but at least heuristics. We have seen some numerical experiments in this problem, and they work at some point. And of course, future is bright, but there are many different possible applications and spin-off for this work, and we are already working on them for giving something more interesting based on this original, even though risky, idea. That was it from my side. I'm open to take any question. Please, if you haven't already, note the number or scan this QR code to find the paper. And this is already in a review process for a journal, for a scientific journal. And if there is anything any answer that I can give to any question, please let me know. Thank you very much for your attention.
Okay, thank you so much. I actually have one very quick question. So in your numerics,
Yes.
what platform are you running it, and how long it takes? With this size of numerics, how long it takes? In
Okay,
which machine? On your laptop, or are you using any like cloud computing?
So the standard time for one instance was about, I don't know, in the order of hours, like a couple of hours or so. And I was running it in a cluster.
Okay.
But in a cluster, but this I don't know the specification of the cluster, but it is not about having a very particular machine. It's just a large machine that allows you to put several instances at the same time and running all of them in parallel.
So it probably takes weeks to collect, to get to plot.
Well, no, not that much. Once I had all the simulations ready, a couple of days were enough to collect all the data.
Okay.
With the machine at several parallel executions at the same time.
Okay. Good. Yeah.
Sunny, do you have a question? Okay.
Thanks for the nice talk. Can you hear me?
Yes.
Yeah, actually, I'm also doing something very similar to this project in the last weeks, and I have some questions. So like, have you ever considered some transportation of the phase? Because if you measure a circuit and the phase will just disappear, and how you construct this phase in the following circuit, like in the initial state, you will have a phase from the previous circuit, ideally.
So okay, let me see if I can get it. So you're mentioning that how can I compute this number that is a complex number, right?
Mm-hmm.
Okay, so the main okay, so I mean this is considered, and the short answer is use Hadamard tests.
Mm-hmm.
So the Hadamard test is efficient. You have to compute this U1 plus some auxiliary qubit and then make them interact via entangling gates. And this allows you to compute both the real and imaginary part of it. So it's a small overhead, but you can get both of them. The crucial part is still compute the Hadamard test for which P. That's a catch. So yeah, I agree that when you measure, you cannot get this number, but just its module, its modulus. But with the Hadamard test, you can get the real and imaginary parts.
Mm.
Yeah, in the paper it's explained in more details. But basically, you prepare the B in advance, compute Hadamard test for real, Hadamard test for imaginary, and then combine them all together. And there is also an error analysis in the paper on that thing. How many measurements you have to perform to avoid having a large error.
Yeah. Okay. Yeah. Because we also like test some Hadamard tests for this issue, but yeah, we for now we are just encountering some problem. Maybe it's just technically problem. Yeah. And yeah, thanks. And another quick question is, have you ever considered some noise in your problem? Because if you want to make a circuit short, a main motivation is that your quantum computer cannot have very deep circuit due to some noise, and this method can like imagine some kind of error mitigation method because it can reduce the depth. And if so, and there will be some computational overhead in your method, obviously. And have you ever like compare your computational overhead with some other error mitigation method?
Okay, so in the realm of noise, the only noise that we have considered is the sampling noise appearing right here in the measurement. In case of more realistic device-dependent noise, we have assumed the probably optimistic scenario of my computer is perfect until the final depth is reached, and then it gets destroyed. So I have to I have to stop computing before reaching that that limit. So we are always assuming the case of pure states, perfect pure state, no decoherence, no anything, and thus we have not compared that with any other noise description of the method. And the reason is basically, well, this method has a lot of possible handicaps, even in theory, even in the perfect case. And well, we designed the strategy of let us try to solve these problems in the sandbox now before going out to the real world and get killed.
Okay.
But it is something that we have to cover in the future.
Oh, okay. Oh, thank you. Yeah. And sorry. Last quick question.
Please go.
Yeah. So maybe you have mentioned, but I forget. So have you ever compared the computational overhead like to the circuit you just don't chop? So what kind of computational overhead of this method is present? Is potentially exponential, or in some cases it can be polynomial or something?
Well, the computational overheads come from two different sources. The first one is the Hadamard test, which is just a linear overhead, which it's not very large. And the second part is the combinatorial thing here. And this exponential overhead is the main killer of the algorithm.
To find the R?
Yeah, exactly. So to find the R, in principle, in case it exists, it's just polynomially hard. Even though it can be polynomial with a high degree, but just polynomially hard because it relies on optimization methods that are only polynomially hard, and so on. Of course, at some point, I don't have the numerics and I don't have an exhaustive analysis of this, but basically we are comparing, say, small exponential against large polynomials. At some point, there will be a gain. But at the very beginning, from now, I'm pretty sure that even in the case of simulation, we are losing the efficiency of the race of efficiency. But we are confident that that there will be some time in the future where we can win this race. And this is
in some particular cases, with some particular problem. Yeah. Okay. Yeah. Thank you.
Okay. Thank you for a nice talk. I have a few questions. Maybe you mentioned, but I'm not fully sure. Like if to write the computational basis which is best suitable for these ansatz or the state you prepare, it's like you rotate through R, like in the MPS language. And if you find R, you can find the best computational basis, but you are using the sampling method to efficiently find how many bases are necessary. So is that understanding correct? You are using.
So it might be, but I don't see it in that way. So what I see is I'm here. So what I'm seeing here is I'm always measuring here in the computational basis. That's my standard measurement. And this R gives me another basis which is more efficient than the computational one. So it performs a change of basis to something that fits my state. But yeah, you were mentioning something about the MPS.
I mean, if like a matrix, the best way to describe it is use the singular value, singular vector or eigenvector. So it means you rotate to that basis, then you need the smallest number of state you need. But in principle, you cannot know R, right?
Okay, it's a optimal thing is with MPS, it's optimal in the sense of the entanglement. But in that case, in this case, we're not interested in optimizing the entanglement, it's just optimizing the description. There has to be a polynomial translation into this low CB rank states MPS. So that thing exists. But to me, there are different perspectives, different way of representing a quantum state. In the case of MPS, in my view, MPS it's a way that fits very well the requirements of a physicist. I'm a physicist, by the way. So it fits very well the requirements of a physicist, where the important number is the entanglement. And it's a physical concept that can be understood conceptually. This case, however, looks more from the computational complexity point of view. So it's more the view of a computer scientist. And at some point, they both need to overlap, and there has to be a nice coupling between both. This is just to be explored. But to me, they are like the two different sides of the same coin. And let me give you an example to explain, to illustrate this observation of yours. So you say it's very the optimal representation the optimal representation of a state is via the Schmidt decomposition, right? So imagine the bell pair. This bell pair is entangled, and its optimal description in terms of entanglement is just the Schmidt decomposition of maximally entangled states. However, I can transform a bell pair into something much easier by using C0 and Hadamard, by just inverting the thing. And this other representation of bell pair, which is 0 plus my unitary operation, is not optimal in the sense of the entanglement, because it does not have any entanglement. So all the entanglement is in the operation. It's an interplay between the operation and the initial state. So I'm not entirely sure that MPS are the optimal way. So let me rephrase. I'm not entirely sure that the optimality imposed by MPS is exactly the same as the optimality imposed by small CB rank. And this like the compatibility of both definitions is still an open question. But it's a very interesting research direction, I have to say.
Okay, thank you.
Could I jump in? So looking at this slide, right? So I think your final kind of like target is the distribution, right? So you want somehow to come up with a set of basics such that the overall distribution is close, right, up to epsilon. And I think if that's the case, there are techniques for example, using classical shadow, right? So as long as you allowed like this small amount of entanglement measurement, then using this classical shadow, you could, if my memory is correct, you can significantly reduce the size of your measurement. Am I right? Minjian, you are reading classical shadow paper, right? I think classical shadow is quite powerful if all you care is the distribution at the end. and you could actually use much smaller set of measurement to simulate that.
Yeah, well, in the case of classical shadows, the way I understand the classical shadows is you can only retrieve some partial information from the state that are basically, in order for it to be efficient, like trace of state times an operator with a small locality. That it scales exponentially with the locality of the operators that you want to measure. So you can compute all the low locality operators at the same time, but you cannot say anything about operators with high locality. And that gives you one perspective of the information that exists in the set. Sorry, in the quantum state.
Okay.
I'm not confident this is exactly the same as the information that you can retrieve from this low CB thing. So to me, all these descriptions, these efficient descriptions, say MPS, classical shadows, restricted Boltzmann machines, reduce-and-chop, entanglement forging, all of them will probably overlap in some regions. For example, for the product states, I'm pretty sure that all of them are very efficient. But there will be some regions of the Hilbert space that can be explored by one of them and not by the other.
Okay.
In the case of MPS, it's quite clear that the region of states that it explores is regions with low entanglement. That's it. In the case of, for example, Clifford simulation, stabilizer simulation of circuits, it explores the set of states computable without T-gates. In the rest, I'm not so familiar with the intuitive results, and I don't think it's that clear. Okay. Exploring the interplay of all these regions is an interesting.
Yeah. Maybe Mingjian, you can take a look, because from the formulation here, I think the idea is that originally you have a rank 1 projection, right? So given by B. And what you really want to do is that you want to come up with a more efficient kind of like measurement so that the distribution is close. And I think this is exactly what this shadow idea can be used. But maybe I'm wrong. Mingjian, you can take a look since you're already reading this classical shadow idea.
Yeah, I will look in more detail and maybe discuss later. I think Adrian's are right, because the shadow tomography are describing some property with some interested observable, like local observable, but here is more like to have the distribution itself. But actually, this is related to my next question. Do you think, Adrian, do you think how it can be used in the variation quantum circuit in certain problem? If we already know we are interested in some kind of the measurement, like some observable or some Hamiltonian energy, is this technique useful to combine with them?
Well, I would not like to answer this question with a lie. We are exploring it, and we have several candidates and several recipes that might be useful for these states, for this representation, that inherit the idea, not exactly the method. But this is still a work in progress. In any case, what I can tell you is, well, see this Venn diagram that we were discussing before. So since this is all the states, this is the set of states that we can mimic, of course, in these states, there has to be some optimal in a variational setting. So if your optimal of the VQE for whatever reason is here in this area, then this method is not going to work. If it's here, however, then we have a chance. And in any case, we can always optimize over this set of states. But still, the details, technical details, and the exact implementation is a place to be explored yet.
I see. Thank you. I have another question about your stage. Why you try to find an algorithm to the stop criteria is that when the rank, the CB rank is below some threshold, why the schedule approach can help if you do not gradually activity optimization? I mean, how does that help?
I'm sorry, I have to ask you to repeat it because I'm not I was not receiving the message very well.
How's the optimization divided into different steps help your optimization? You mentioned, gradually activating optimization. Yeah, this figure.
So basically, this avoids the following problem. So I start with a random value of theta, right? A random thing. And then I tell my optimizer, please take this function and optimize it. The problem is that computing this function itself, which is the CB rank, can, to the best of my knowledge, can only be done through sampling. And if this sample has to be efficient, then the CB rank can only be estimated if it's small. So at some point, what we end up having is a landscape or a function that returns either low values or non-numerical thing. And this optimizer tells, well, I don't know what to do with this. There's no possible way I can distinguish a CB rank of 2 to the n or a square root of 2 to the n. There is no possible way of distinguishing them. So if you feed the optimizer with this, you are not going to go anywhere because the optimizer is not capable of extracting any information from there. This cut and thrust strategy avoids this problem by exploring only the regions of the landscape where the CB rank can be efficiently estimated.
Okay, I see. Thank you. Sorry, my final quick question. The rotation is it supposed to be single gauge rotation or is a general rotation? There are some.
In our case, it's supposed to be in these experiments are supposed to be this particular ansatz, the one in the right. Of course, you can design your own R. You can, in fact, a very interesting question is what kind of states I can represent efficiently modulus a given R, for example.
So each time you have to decide your form of R before the simulation, right?
Yes.
I see.
And probably having some previous knowledge of the states that that are available will help.
I see. Okay, thank you very much. Okay. So since I'm the host, is there any further question from the audience? Okay, I think okay. Yeah, thank you for the very nice talk and all the discussion. Thank you very much.
It was my pleasure. And
thank you.
Please, probably Leandro knows my email for sure, and Mingshu, am I saying it right?
Mingshu? Yes, Mingshu, yes.
Has my email as well. So please, if you have any doubt, any comment, any suggestion, or just want to step by and say good afternoon, please don't hesitate in writing.
Okay.
I'm always open to answer all emails.
Sure, thank you. We will get in touch. Okay.
Perfect. Thank you very much.
Bye.
Nice.
Bye.
Thank you. Okay.
Goodbye.
Bye.